And we get introduced to something that isn't used a lot in pre-calculus, but it does get used a fair bit in calculus and later on, so it's important to get introduced to it. Something called piecewise notation. And it's used when you have a function that looks different over different parts. So for example, we mainly graph functions that all look the same, like a parabola keeps its shape all the way along. But what if you wanted to have a graph where it was like part parabola, part line? What would you do? What happens if the parabola was only up to here and then it changed into a straight line after that? Well, what you would do is you would break up your domain and say, when the x's are on this side, you graph your parabola. When the x's are on this side, you graph your line. So how do we write that? And they've got a very simple example here that's not in your textbook, but it says, you want to enter a park, and they have discounts. It costs $10 per person if 1 to 9 people go. 10 to 99, it reduces to $8. And if you can get 100 more people in your group, right, then it's $7. This would be really good at Disneyland. I'd be there first thing in the morning, and I would say, yeah, all these people in the lineup, they're all part of my group. It's like 500 of us. So we all have to pay $7 instead of $10, right? But probably they wouldn't let me do that. The way that we would write this is that we write it with a big sort of bracket here, and we have piece 1, piece 2, piece 3. Piece 1 happens when it was between 1 and 9. Piece 2 happens between 10 and 90. And piece 3 happens when it's bigger than 100. So what you're doing is this part here is restricting the domain. That's more intense. Okay. So absolute values, this you have in your textbook. An absolute value equation is really, when you look at that V that we've drawn, it's really two different lines. One line stayed the same, and the other line got flipped up. The line that got flipped up, right, if you think about your regular absolute value graph looking like this, this is the one that we did in our construct the understanding to start with. Well, if x is bigger than or equal to 0, it didn't change. That's just your line y equals x, which would keep going. But when x is less than 0, now, what line is this? That's the graph of negative x. And anytime you flip a graph up, all you have to do is multiply by a negative. Numerically, do you see that this works? If x is 5, it falls into this section. What's the absolute value of 5? Just 5. If x is negative 3, it would fall into this section, and it should equal negative 3. And 2 negatives makes a positive. Isn't that the same thing that the absolute value does? So now what we're doing is we're writing the equation in 2 little pieces rather than the whole thing. And just figuring out which sections are which. So now we can go to our last example. And graphically, we sort of have to figure out where's the x-intercept, because that's where the graph flips. So if I just first of all graph, right, first of all in blue, I'm going to graph y equals 2x minus 1. Can you see that that would have a y-intercept of minus 1 and a slope of 2 So it goes up to over 1, up to over 1, and this would be the line. The most important point will be this x-intercept. When y is 0, roll it down badly here. When y is 0, x has to be a half. On this same one, if I graph the absolute value of 2x minus 1, using the skills that we had before, this part stays the same, but the flip happens right at that x-intercept. And the key is figuring out where does it change? It changes at that x-intercept. So y equals the absolute value of 2x minus 1 is the same as y equals this fancy squiggle bracket. It stays the same, it stays 2x minus 1 if x was bigger than or equal to a half. And we flipped it, which we would put a negative out in front of the whole thing. So I put a negative with brackets, because you can distribute if you like, but it's kind of nice just to write it like this. As an idea that I flipped that whole line, which means I put a negative out in front of it, if x was less than 1/2. And in piecewise notation, you make the equal sign go with one of them. It really doesn't matter which one, because that's where it's equal to 0. But we don't let it include in both, because it's kind of like, which equation is it? When it's at a half, you have to pick your favorite. I don't know, doesn't matter which one. So in part B, if you were graphing this in black, if I was first graphing the inside, again, I'll graph the inside in blue. And are you okay if I factor it already by taking out a negative x and get negative x times x plus 3? What's really nice about that is you will find that in factored form, you can find one x-intercept is at 0 and one x-intercept is at -3. Which way does this parabola go? It goes down. So I'm not even going to graph it completely accurately. I'm just going to get a sketch of it. I know that the vertex is going to be there in the middle at -1.5 comma something. So that'll be my graph. Now the absolute value, this part would stay the same, and this part would get flipped up. This would be the graph of y equals the absolute value of -x² minus 3x. So how do we write this in piecewise notation? Can you see that it didn't change? This part in the middle didn't change? When did that happen? If x was between -3 and 0. That's where it didn't change. Where did it change? And when you change it, when you flip it up, it's like multiplying by a negative. if x was less than -3 or if x was bigger than 0. So this is writing a graph in piecewise notation. Student circle questions 8, 9, and 13.